In this lesson, we want to talk about designing data. Now, this is going to be sort of a conceptual bonus for you in this class in that there's no exercise tied directly to this, and in the final project you're going to be doing in this class, we've really done this work for you. But I wanted you to get a sense of the fact that there is more to the idea of designing an application than just the visual design. Hopefully this is not a new concept to you, and that you're probably aware of the idea of user experience design, and that we're in that situation thinking about how the application should be structured, what kind of information architecture we might use, what the interaction design might be like, all kinds of uses of the word design. But even when we get to the simple fact of having data coming in and out of our system, we actually have a whole discipline devoted directly to this idea of designing data. So wanted to have you take a look at a little bit of that by way of a cursory introduction. If this piques your interest by chance, it's a good thing to set in the back of your mind for when you take Web Design 3, and that you'll have an opportunity to do some experimental projects in that course, in which case you could experiment more with this idea of designing data. But particularly if you intend to work in an interactive setting, being familiar with, at least having heard some of these terms, is better than never having heard of them, but certainly something that you don't have to completely understand to succeed in this field. All right, those disclaimers aside, let's take a look. As an overview, as we move from the mechanics of JavaScript into planning a simple application, a key element to consider is how the data that drives our application will be structured. We first need to understand the data cycle of create, read, update, delete, and we can then consider how to design our data sources using entity relationship diagramming. So we're going to be looking at that create, read, update, delete cycle, and then looking at entity relationship diagramming. So first of all, the data cycle, which fits the acronym CRUD, create, read, update, delete. Many applications involve a common cycle of data that includes the following stages. First, data needs to be created. Data can be generated in the application, such as through a data entry, or through some form of user interaction in the system. And in some systems, we actually create the data ourselves as administrators of the system, and then maybe users continue to populate additional data or different forms of data. But one of the next crucial things that most applications will do is to actually read data. That is, that data is loaded and displayed to the user or used in the system for logical processing of some sort. All we're meaning to say here is that, for the most part, we're going to want to show information to the user. We call that reading data. Then we also logically might want to be able to make updates to data. So particularly if we've allowed users to create data, they could make a mistake on accident, or something could change and they want to be able to get in and update that entry. Well, that's what we're talking about with the U, update. Data is modified through use of the system. So there's sort of passive updates where just by logging in, you update your user entry maybe, where the last time you were logged in is stored. That's kind of like a passive update. Or you might, by checking the box on something, be making an update to it, as opposed to clicking to edit something and editing the text in it, where you feel like you're more directly actually editing that thing. So lots of ways that updates can take place. And last of all, if we want them to be able to create, if we're going to allow them to update, there's a chance that they accidentally create something they just don't want altogether. Or there are times where we, as designers of the system, recognize that some item needs to be destroyed as a part of the application process. So we also have the D for delete. Some forms of data must actually be deleted to maintain an efficient system. So that is the CRUD system. We're going to be able to read information. We're going to want to be able to create, update, and delete that information. Now, not everything in the system needs to have all four of these pieces, but let's just imagine an application that allows you, the user, to log in and create lists of things. So you, as a user, might want to create a list, which kind of is a container itself, right? and then you might want to put items onto that list. So in the system, there will probably be a user, which you create when you create the account, but do you ever delete the user? Well, maybe sometime you say, I don't want my account anymore, and you kind of ask the system to delete your account. But really, we don't actively think about our actual user as an entity in the system. Nonetheless, it is. However, we do think about creating the actual lists and creating the items inside of the list and making all kinds of changes to those. So with that example in mind, let's move on to this idea of data modeling. So this is that data sources must be designed just as thoughtfully as the interface itself. We really want to put thoughtfulness, intentionality into the design of the data so that we build something that considers all of the data we know about, all the different pieces that we're going to need in our system, as well as account for the fact that it could grow and change over time. So we want to have efficiently designed systems that are ready to easily be adapted. Now, the process of designing data is also called data modeling. A common form of this is the entity relationship diagram. Okay, so this is basically a way of planning out and depicting the data that's going to be behind our systems. And it is used by database administrators to create the databases, and it's used as a communication tool between developers and between developers and designers so that we all are on the same page about what kind of underlying data exists in our applications. So entity relationship diagramming. This analyzes the data needs and organizes each piece of data as a property of an object or entity. So we've been working with objects in our JavaScript course so far. In a way, what we're doing now is just kind of creating a diagram that kind of outlines the objects that we can use in our system, rather than just kind of creating them on the fly in JavaScript or just assuming that they'll always be the same from our database. We like to create a little diagram that helps us visualize this better. These entities are designed with something called cardinal relationships to each other through a process called normalization. We're going to unpack those things here in the next few slides. And then these entities and relationships are depicted using boxes and connecting lines with intentional symbols to indicate relationship types and special fields known as keys. So we're going to unpack all those different pieces, but just giving you a heads up that there's kind of a whole system for doing entity relationship diagramming. Okay, so part one is simply to brainstorm the kind of objects or entities that you need for your application. And so what we'll basically do is start by drawing a box for each of those entities. We'll place the name of the entity at the top of the box and put an underline beneath it to kind of separate the name of the entity from the next piece, and that is the properties. We're going to list those properties below the name, basically under that underline. And we're going to note any non-string data types in parentheses beside the property. So we'll assume that each of the properties is going to be a string. But if we want any of them to be something else, like integers, it's a good idea to kind of note that in a parentheses. Finally, we can draw lines to connect related entities or kind of demonstrate that they're connected in some form. So here we have this list system that we mentioned a moment ago, where we might have a user represented by the person entity. The person can create lists, and the lists will have items in them. So you can then see each of those three entities listed here. And then the properties that we've imagined might be a part of each. So the person, we might want to have a first name and a last name, an email, and an address. The list itself might have a short name and a longer description. And then each item is simply going to have the content of that item. Okay, so those are the entities, and then you can see we've just drawn a line from one to the next to indicate that a person is related to a list, in that I might own a list, or somebody else might have shared a list with me, and so I kind of am related to that list in some way. And then the list items go into the list in some fashion. So there's no direct relationship between a person and a list item. We only establish that by relating a person first to a list. All right, now this is just one way to design the system. Of course, it may be that in an actual system we would want to track who created the actual item itself, but In this system, we're not tracking that. Okay, so let's talk a little bit more about those relationships, the connecting lines. And we think about relationships in terms of something called cardinal relationships. There are three kinds of cardinal relationships: one-to-one, one-to-many, and many-to-many. So with one-to-one, that is that one instance of an entity is related to one and only one instance of another entity, and vice versa from the other direction. These are rare, but most often used to create entities that are smaller and more focused. One example of this might be the relationship between you and your student ID card. Those are two separate entities, right? There is student ID card and there is you. And when the system is working the way it's supposed to, you should only have one ID card, right? I don't think I've ever heard of somebody who ended up with multiple ID cards. I suppose it's possible if you lose it and get a new one and then later find it, you might end up with two. But like I said, when the system is running normally, you should have one ID card. So this would be considered a one-to-one relationship. There is you, and there is your ID card, and there is a one-to-one relationship between those two entities. Okay, a much more common relationship is the one-to-many. This is that one instance of an entity is related to many instances of another entity. But when we think about it the other way around, one instance of that other entity is only related to the one instance of the original entity. I know that gets a little bit strange when we try to explain it that way. But you can think of it in terms of a mother and her children, in terms of a biological mother and her biological children. A mother can have many children, right? There is a one-to-many relationship between the mother and her children. But each of those children only has one biological mother. So see how that works? It's a one-to-many in one way, but it's a one-to-one in the way back. Okay? That distinction isn't really crucial, except that you understand that we're not saying in a one-to-many relationship that the children have many mothers. That's the kind of the crucial difference. One mother has many children. Each child only has one mother. On the other hand, a many-to-many relationship is one where one instance of an entity is related to many instances of another entity. And that same idea works backwards the other way, in that one instance of that other entity could be related to many instances of the original entity. Okay? And the convention in order to accomplish this is to use something called a lookup table, which you'll see in a moment. So what's an example of a many-to-many relationship? Okay, this might be an example could be that, let's see, throughout your time at the university, you might have lived in many different college dorm rooms, right? So the relationship between you and the dorm room entity is that you have been in many of those dorm rooms. And the same is true the other way around, in that any one of those rooms could have had many people. So let me try to say that a little more clearly. We would imagine that there is a person entity in our system and a dorm room entity. So in the person entity, we have a list of all the different people. And then in the dorm room entity, we have all the different dorm rooms. So any one person could be associated with many of those rooms for their time at Cedarville. And any one of those rooms could also be related to many different people in that, you have roommates perhaps, and of course there are also other people who have lived in that room in different semesters. So that's where a many-to-many relationship can come into play. All right, so a little bit confusing, but now you've at least been exposed to the ideas. Maybe you get it and you're great. If you don't get it, don't worry too much about it. Just let it suffice that you've heard of the terms and might be able to do more with them down the road. So here's how we depict these relationships. I have drawn them very explicitly here to help you get the idea, but these symbols are kind of a pain to draw in Keynote, so on following slides I've simplified them. But the idea is that the crow's foot looking symbol represents a many on either side, and the straight line it represents a 1. So we have a many-to-many relationship between person and list. That is to say that a person could have many lists, and any one list could also be related back to many people, so a many-to-many. On the other hand, a list can contain many items, but each item can only be a part of one list. So one to many in that situation. And we have not depicted a one-to-one here, but we will see later on where a one-to-one could be helpful. So that is the 3 cardinal relationships. Now, let's talk about how to optimize our data design here using the process of normalization. Normalization is a process by which we ensure our data design is reliable, flexible, and efficient. So let's think about each of those words for just a moment. What makes something reliable? Something is reliable if you can count on it being always true, if you can count on it not having any errors, if you can count on it being stable. So think of all those words in terms of reliable. And when we think about making data lists, what are things that can happen with data lists that could make them unreliable? Well, there could be user error in the lists. There could be accidents in the system that lead to something not being entered. So things that come to mind are, of course, spelling errors, transposition of characters, or just plain mistakes, as well as things like accidental copies or pieces of data being deleted. So we want a system that's going to be lightweight, that is going to be easy to look at and tell if something is wrong. Okay. Related to that then are these ideas of flexible and efficient. On one hand, flexible means that we should be able to modify it and change it and make it adapt. So another good case for it to be lightweight and really kind of thinking about that flexibility. And of course that brings us naturally to efficient. When something is lightweight, when something is ready to be flexible, we also think of it as being lean and assembled in such a way that there's no repetition, there's no, or there's minimal repetition at least, so that we can just really keep it trimmed down to what's necessary. So we don't want to store extra stuff that we don't think we'll ever use, and we want to be careful about how we store the stuff that we do need. So to do normalization, what we do is walk through 3 different steps called the normal forms. Now, first normal form is the only one that is really considered required and necessary. Second normal form is a best practice, and third normal form is usually just annoying. But they're all helpful, and so they're worth talking about, even though annoying. Third normal form can certainly continue to improve. They also build on each other. So we do most of the work in first normal form. This is where each entity needs to contain a unique primary key. The idea here is that we need to make sure that there is at least one property that is unique for every entity in that field. That way we have something that we can select a very specific item out of that entity whenever we need it. So this relates to the idea that you might be used to in HTML of having an ID attribute. That is the unique attribute we can use to select that one specific thing. Okay, so when we design our data, we want to think about whether or not our entities have a field or a property that is guaranteed to be unique for each of the items in it. So this is not natural for all entities. If you think about how you might describe a person, you might think immediately of their first name and their last name. But we would readily see that neither of those things are always unique, right? There are many Johns in the class. There are many people with the last name of Smith, okay? The combination of the two isn't always reliable either, in that as unique as my last name is, there are other people in the United States who have the last name of Shanley and also who have the first name of Philip or Phil. So first name, last name is not unique enough when we're talking about people. We typically might then start to think about things that are more unique, like our fingerprints maybe, Well, how do we account for fingerprints in a system? That becomes kind of complex and challenging. So what we often find we need to do in order to have a unique way of identifying any one entity is to use something called a auto-incrementing key. And this is to simply assign a random number or a number beginning at 1 and counting up automatically for each new entry. And so this is actually what's at play in your student ID number. If you compare your student ID number to one of your other friends, you'll likely find that one of your ID numbers is kind of a lower in the numerical list than the other. And that simply means that if yours was lower than somebody else's, that you were entered into Cedarville's database before somebody else. So for example, mine begins with 133, and most of yours probably begin with a 2-0 something rather. We may even be to the point where some of you have a 2-1 at the beginning of your code. That simply means that mine was entered much earlier than yours, logical. But if it turns out that you happen to have a 133, that may be because you have a relative or maybe even a parent who came to Cedarville around the time I did, and that you were entered in the system as being related to one of those people. Chances are you weren't around when your parents were here. But if you had a sibling, one of the things Cedarville does is asks who else might be related to you that might be interested in coming to Cedarville someday, and those people sometimes get entries in the system. All that to say, the number increments by 1 for each new person added into the system. And so you can get a sense of how long you've been in the system when you compare your ID number to somebody else's ID number. The auto-incrementing key is one thing we do. We simply assign a number to each item and make sure that that number increments by 1 for each new entry, and then we therefore have a unique way to recognize that item inside of that entity. So identifying a primary key is one of those crucial things that we do in first normal form, and you'll see this applied to our design in just a minute. Then we make sure that each field on a given entity, or each of those properties, contains a single logical or sortable value. So what we mean there is we want to look at the fields that we have identified and make sure that basically the data that would go into it is simple enough that it doesn't have too many pieces we would want to separate out in order to sort them or do things logically with them. And you'll see in our diagram that a case where we want to do this is with the address field. That's on one hand pretty vague in that there's all kinds of pieces we might put into an address, but it's also kind of unwieldy. If we have the entire address, city, state, zip code, street address, in one field, we wouldn't be able to sort by the city if we wanted to kind of see all the people from one city or from one state. So we might want to actually break those out into separate fields. So you'll see that in a moment. And then last of all, we want to move any fields that repeat a similar kind of semantic data into separate entities. So this is where we're going to kind of think about what all those fields would look like. Oh, sorry. What I mean there is we want to avoid having a table that has columns that have similar data that repeat. So for example, if you this is why on our list, for example, we did not. We had a list, as in the container that we put list items into, and then we had a separate list item field. If you didn't do that, your list entity might try to keep track of the items. So you might have the name of the list and the description of the list, but then you might try to have a property like item 1, and then item 2, and then item 3, and item 4, and those might all be properties of the list object, and that just doesn't make sense. It would be much more efficient to have a separate entity that we can grow and shrink as much as we like. It becomes very unwieldy to have a table that has 10 different list item fields associated with it. Another example would be to imagine that, if you're thinking about keeping track of the members of a sports team, you might think to yourself, oh, well, I only have 10 players on this sports team, so I'm going to have an entity that is the team, and it's going to have the name of the team, the coach's name, and then the each of the players' names, player 1, player 2, player 3, player 4, player 5. Well, so how do you decide who's player 1? How do you decide who's player 2? Do you put them in alphabetically? What happens if one of those players leaves the team? Do you now have to put the new player in their place? Or are you going to shift all the others around and then put the new player at the end? Or it just becomes a pain. It's not the way databases need to work. So instead, we would pull that out into a separate entity. So we've shown you here how first normal form could affect the diagram we had originally, in that over on the left with the person entity, we had a address field. Well, we recognize that we ought to break that up into sub fields, so we broke it out into street, city, state, and zip. You can also see in each of these that we added a unique primary key. That's with the red and the bullet. A bullet or some kind of symbol is also often used to identify a primary key, and that is the single field that uniquely identifies that one entity. Now, where we have relationships, such as between list and list item, we also need to account for that relationship. So how would you identify a list item as being a part of a list? Well, you could simply include that list's primary key as one of the properties of list item. So we could have this table of list items with their content and their own primary keys, so that each one, gets a unique number. But we could then relate it to the list that it belongs to by using that list's primary key here in that table. So the orange field there with the hollow dot is called a foreign key, and that's foreign for logical reason. We're bringing in some other entity, a foreign entity. We're bringing in their ID here so that we can establish a relationship between them. Okay, so this is where we get to now the relationship between person and list as being a many-to-many relationship. That would actually be impossible to do in terms of directly with the fields. In order to have first normal form, we would not want to have a list entity, for example, that has a whole bunch of person fields that relates it to some number of persons. Likewise, we would not want to have on the person entity a whole bunch of fields that allow it to be related to one or more lists. Instead, we need a lookup table that fits between them. In the lookup table, we simply pair two foreign keys, the list ID and the person to whom it belongs. And if you think about it, that combination would always be unique. We would never need to relate one person to one other list multiple times. Now, anytime we have a person in here, it is likely that we would have a different list ID associated with them in order to let a person own multiple lists. And vice versa, if we want to share a list with multiple people, we might have that list ID appear many times, but each time it appears, it'll be paired with a different person. So there we have accomplished first normal form, and we have updated our fields to show all of this. So that was most of the work. Thank goodness. Second normal form is where we first ensure that all entities are in first normal form. Right, so it's really just a way of saying, okay, first normal form was really the required stuff, and now we're adding on an optional best practice kind of layer, and that's where, to get to second normal form, we add to first normal form that we reduce unnecessary repetition between the rows or instances by creating separate entities that encapsulate such data. So what in the goodness gracious am I talking about there? Let's consider that address set again, particularly the zip code, the state, and the city. If you think about it, when we enter a zip code, and if you imagine a spreadsheet with zip codes kind of going down across all the different rows, each time you have a zip code, you're very likely to have a very similar set of state and city in the accompanying fields. So there's basically going to be repetition of zip codes going down your spreadsheet. And for any one zip code, very likely you're going to have a bunch of repetition of states and cities. Okay, so what we could do in order to make this into second normal form would be to pull out that repetition, leaving only the zip code in that person entity, because zip code now becomes a foreign key for a separate entity where we have tracked all of our zip codes. And for each zip code, we've put in what city and state it belongs to. Now, this is an imperfect model. There are lots of different ways that zip codes are treated, but hopefully it's an example that shows you how this second normal form idea can affect things. And notice that what that did is made the person entity just a little bit smaller. All that's remaining there for that set of what used to be 3 fields is 1 field. And we are now no longer repeating all the state and cities for each of the zip codes. We're putting them once in the zip codes table, and we're only putting the zip code in as a foreign key in the person entity. Okay, so we didn't have any other places where second normal form was needed in this diagram, so let's move on to the last one. This is the one that I mentioned can be just plain annoying sometimes because it's really getting to be nitpicky. So first of all, we want to ensure that everything is in second normal form, which of course means it's also in first normal form. And now we're simply going to separate distinct semantic entities. So this is where we're going to look at each of our entities that we have and ask, are all of the properties really necessary to be part of that semantic thing? It's likely that those properties relate to that thing, but do they belong on that thing, or would they be better pulled out as separate things? So once again, let's pick on that address field. In that the address is part of kind of the contact information for a person. Is that contact information, does that have to be part of a person? What are the most core things about person in our entity? Well, probably first name, last name, and their primary key are about all we need. But email and street and the zip code are sort of contact information that we could pull out into a separate entity. In this case, we likely have a one-to-one relationship between a person and their contact information. And then, of course, we have kept that person contact efficient by keeping the zip codes separated. So you can see this just gets a little bit nitpicky, and sometimes it's very helpful to make sure that we have teeny tiny entities and are streamlined as possible. Other times it really creates just more things to work with than necessary. But now you see the gist, and you've been exposed to the full, not the full. You have been exposed to an introduction to this whole idea of data modeling, data design, and using entity relationship diagrams. We will be coming back to the CRUD system in upcoming lessons, so if anything you take away, note above all that we do care about how we structure our data, and we put a lot of time and thought into that, because we're going to need to work with that data in those 4 different ways: create, read, update, delete. So look forward to those coming back in the next lesson.